Thank you very much, Ian, for that introduction. Right. Let's see if we can get this working. Right, what I'd like to talk about today then is how we're using distributed acoustic sensing, that's using the fibre, in a variety of seismic applications. And I'll also kind of hint at what else we're using it for in upstream applications, and there's quite a variety of different tasks. So we'll show you the primary use at the moment, which is for vertical seismic profiling. I'll show you some of the microseismic detections that we've seen and how we can exploit that, and also how we can use this in the future for surface, both on land and potentially for permanent reservoir monitoring systems. So I'll talk about who we are, I'll talk about what distributed acoustic sensing is, we'll talk about some of the deployment aspects, which are quite important because it's flexibility, and then we'll talk, as I say, about the three different types of measurements and some of the future developments. So as Ian's already mentioned, OptaSense actually comes out of a company, it was originally Defence Evaluation Research Agency. It was then about 11 years ago renamed Kinetic. Kinetic's about 9,000 people worldwide. OptaSense was taken out as a wholly owned subsidiary. We're currently about 160 people, offices based in the UK, but we've got offices in America and in the Middle East and in Australia now as well. You can see one of our field operations here in Calgary. So what is distributed acoustic sensing? Well, I'll get one of our sensors out here. This is actually, every result you see today is recorded on one of these sensors, and I can hardly carry it. There you go. Can you actually see it? Probably not. But we're just using single strands of optical fibre. Now, unlike some other fibre optic systems you may have come across in the past, where they're coiled to make geophones or they're wrapped to make hydrophones, we are just using the fibre in its straight condition here. And we've got no other delineating components in it. So we can take any standard single mode optical fibre and use our technique on it. And I'll reinforce the fact that every single result you'll see today is recorded on one of these fibres. So there's a tremendous advantage on this. We can measure, we can put this cable from the top of the well right the way down to the bottom. We can either strap it to the outside of the casing or put it on a production string or use it in a wireline arrangement. And it gives us full bore coverage, so we can see from top to bottom. Now, a normal sensor is obviously, you would see a point sensor. You would have like a electrical gauge or maybe even a fibre optic gauge at the end of the fibre. We can also have quasi-distributed, so this would be akin to a geophone array, for instance. But in a distributed sensor, every single part of that fibre becomes the sensor. I can interrogate any part along its entire length. The fibre is the sensor. There is nothing else there in this situation. So how does it work? Well, it uses a phenomenon, an optical phenomenon in the fibre called Rayleigh backscatter. Rayleigh backscatter is the same phenomenon that causes the sky to be blue when you look up at it. And it's created by these very small defects in the atomic structure of the silicon lattice that's within the core of the glass structure. And these defects are enough to create a very small amount of scattering within that fibre, and the amount of backscattered light we actually analyse. So in a situation like this, we put in a pulse of highly coherent laser light into the fibre. The light travels along this fibre, and as it does so, a small amount is backscattered back to the receiver. And we can see this pattern formed for the backscatter along the entire length of that fibre. Now, if we strain a portion of this fibre by a small amount, we actually get a change in that backscatter pattern at a local position. And because we know the speed of light in the fibre very accurately, we know precisely at what point, at what position along the fibre that strain has occurred. So, this is a strain gauge, and all the results you'll see are strain gauges. And we must keep that in mind because the results look very akin to what we'd be familiar with in geophysics from a geophone or a hydrophone. But fundamentally, this is the strain gauge that we're looking at here. So what we can use this for is we can actually interrogate fibres up to, let's get this working, there we go. We can interrogate fibres up to 40 kilometres in length. Currently, we can interrogate 4,000 independent sensors along that 40 kilometre fibre. Soon we'll be able to interrogate up to 10,000 sensors. And getting onto the standards, this does actually create a large amount of data. Quite often we can be generating a terabyte of data a day on just one of these fibers. So there's a huge amount of data generation here. The data is then passed to processing nodes, typically a PC, where we then decimate the data down and turn it into formats which you can use. In the case of the seismic industry, it's always in SegY or SegD formats. So, some of the upstream examples. As I said, the DAS fiber is being used in a multitude of different applications. As outside of the oil and gas industry, we're using it for monitoring trains on railways. We're not the London Underground, unfortunately, today, because it's not working. We're measuring vehicles on roads, so some of the motorways in the UK are being monitored by this, and also pipelines around the world. So there's about 11,000 kilometres of pipelines worldwide have got our fibre on it, monitoring it for third-party interference, and we're also looking at things like pig tracking in those pipes. But in the upstream market, what we're actually exploiting the technology for is in a number of areas. So in completions, we're looking at things like cement cure monitoring, hydraulic frac profiling, cross-well communications, and microseismics, which I'll come on to. In the production, we're looking at production logging and casing leaks and steam flow. And then in the evaluation phase, it's both land and seabeds and offshore VSP measurements. You'll see that we haven't really got any exploration here. This is still in evaluation. This is the tool for evaluation rather than exploration. So a quick word on fibre deployment. Get that working. There we go. It's extremely flexible. So you can put this fibre, you can attach it to the casing as that casing is deployed in the well, and then it's cemented in place. That then becomes a permanent fixture for the entire life of the well. You can attach it to the production string. And we can now use that. We can do, as it's retrofitted, we can put that on our production string, clamp it there, and take measurements. And many of the measurements you'll see from the seismic results we've got here are taken on the string. And also we can use it either in a coiled tubing or a wireline type of arrangement for an intervention, temporary type of deployment. So we've been doing this now we actually did our first measurement at the latter half of 2009. That was the first ever DAS VSP measurement. So it's just over 4 years, 4 and a bit years we've actually been using this technology for now. And we've done equivalent of over 90,000 shots of data have been acquired in that period. And typically we're measuring hundreds of channels per well using this fibre. We were lucky enough fortunate enough to win that award last year. There we go. So all of these shots I show here, they're all taken on one of these fibres. Every single shot you see. So what are the advantages? Well, the first is it's for VSP, it's non-intrusive. Once this is deployed in the well, I don't have to intervene with that well any longer. It comes out through a wellhead outlet. That fibre can be deployed to a control box, which can be several, hundreds of meters away from the wellhead, and therefore I never have to go to that well again to do these VSP types of measurements. It's permanent, therefore I can come back at any time and repeat measurements, which is ideal for time-lapse or 4D types of measurements. It does full vertical coverage. I don't have to keep moving my geophone array. I've got from top to bottom. Retrofittable, I can attach this to the production string on existing wells, and it's robust, so I can use this fibre in very high temperature wells. Wells up to 300 degrees C and above can be used, so some of the new applications we have of this is in SAGD, for instance, where we're looking at this to evaluate the evolution of the steam chest within SAGD and other EOR types of applications. So the system is really, it's now commercially available as a product for DAS VSP. The data we take is fully time synchronized to a microsecond using GPS clocks. We do all of the stacking and correlation in real time, and all of the output is in SegY format. We also have created some tools so that we can actually view this data in real time remotely. So this is a web-enabled tool. It shows the shot pattern, and we can show the individual fibres that we are capturing. In this case, there are 3 separate wells we're being imaged simultaneously, and we can show thumbnails of the seismic sections being gathered on each one of those wells and how they're being stacked and correlated, and then the user can actually click on any one of these thumbnails and bring down the SegWi for full QC analysis. So, how is it being used in the field? Well, you can deploy, as I've mentioned, you can deploy that fiber in a number of different ways. And really, the way you deploy it depends upon the quality of the results you will get. So the best quality you can achieve is when you have it actually cased, cemented behind the casing. You've got obviously very, very good coupling there and a very good response. But we've got, equally, we've got very good responses from tubing, fiber on tubing, remarkably, given the fact you've got this steel tube and an annulus, and then you've got this fiber attached to that tubing, and yet we're still able on that fiber to pick up some usable, very usable seismic results. Furthermore, we can even take it to putting it inside the production tubing on a wireline or coil tubing arrangement, and we can still get usable seismic results. Now, this is not as sensitive as a geophone, so what you have to do is you have to put some more source effort in at the top end. But the advantages of the fact that you've got potentially hundreds, if not thousands, of sensors along your entire wellbore allows you to use that factor to bring the data out and give you usable results. So, as I say, a bit more source effort on the top can give you very similar results to what you would get with a conventional geophone. So this is one of the very first measurements that we did. This is a CO2 sequestration site in Canada called Quest. We were asked to go there back in 2010, and what happened in this particular well is we were deployed behind casing, so it's a permanent installation, and a geophone array was run in that well and clamped to the sides, and we did a walkover in two planes. So we had north-south, east-west walkover of that particular array in the well. And we were then able to compare the results from the results gathered on the cross-sections gathered on the geophone and those gathered on the DAS fiber. And that we were immediately able to see that we got extremely good comparisons between the two. Now, the spectrum, you'll see that there are differences in spectrum. Not surprising, because as I say, it's not a geophone. It's essentially this strain gauge. So there are differences in response. But this was deemed to be good enough to be able to resolve what was actually going to be happening within the reservoir itself as they started to pump the CO2 in there. So then we were invited to come back a year later, from 2010 to 2011, and repeat the survey. This particular, when we repeated the survey, the ground was actually waterlogged, so we could only do one of the passes. But on the one pass that we did, we got a 15% normalized RMS difference between them, which again was seen to be very good repeatability between the two measurements, and certainly good enough for it to be used as a monitoring technology for the CO2 sequestration site going forward. So there are some delays with Quest at the moment, but the hope is this will go fully operational with a full baseline being done later this year. And then they'll start in early 2015, they start pumping CO2. Now, another exciting one, and this is relevant because this is what we're doing at this very moment, is a project looking at this technology for EOR types of applications. So Shell and PDO have a number of EOR projects. This particular one in Oman, they've got a field with many wells over it, but they want to increase their recovery by 5%. So what they're doing is they're injecting lots of steam into the ground. And what they want to know is where that steam chest is going, where they need to put their new wells, and where they need to do infill, and so on and so forth. So they need to image below the ground. Now, the way they wanted to do this was using conventional VSP, but that proved to be too expensive and extremely difficult on such a brownfield site when there was so much infrastructure. So we then did a few tests using DAS, and this is seen as the potential solution, preferred solution. So looking at these results, this geophone array results taken in a well. So that we had the well, geophone array put down there, clamped, and we ran a 3D VSP over the top of that particular well with the geophones clamped. That geophone array was then removed, and then a production string was put down with the fiber on the production string. So now you haven't got anywhere near the same kind of degree as coupling as you had with the geophone. However, if I can try and toggle between these results, you can see this is the DAS result and this is the geophone. So it's not as good. We can see that. We can see that we've lost some of the quality. However, when we process these results together, because of the sheer amount of data that we've got generated by this fibre, we were found that the cross-sections look very, very similar indeed. And that gave both Shell and PDO confidence to move forward of this as a measurement tool for this particular field. So you can see how busy this field is. What we are now doing, as of today, we actually start today, we are actually monitoring 8 wells simultaneously. So there's 8 wells with fibre in. We've got a full 3D VSP going on for the next 25 days over this site. And the contract is to come back for every year for the next 5 years to do a time lapse of this reservoir. And we extend out from 8 wells, we're going to extend out to 12 and then ultimately 20 and maybe beyond. All of those being recorded simultaneously. And that all of those fibres all come back to one unit, one cabin, where all of these fibres come in and we record it all in one location. There are other aspects as well where this is being used. This is in North America. We're using it in a refraction survey. So to save cost, instead of doing a big 3D survey here, they've got a dynamite ring around 3 wells. And because of the formation, we're allowed to do this refraction survey because the sound bounces along, goes through the reservoir and then back up. And we get these kind of results on the fibre recorded again with that fibre on the production string. So when we look at the cross sections, we can see the P refraction and the refraction signals all within this data. So again, this is now being deployed on that facility over the next few years, and they'll be going around every year or so. They'll be going around doing another refraction ring survey to see how that reservoir is developing. Offshore, we've done some offshore measurements. This is a Gulf of Mexico measurement. So this was a full nodal survey was being carried out at the time, just as Fairfield were mentioning earlier. Similar to that, there was 50,000 shots were being taken over this nodal survey. And we were asked to go along and said, well, the rigs which this is happening around have actually got fibre deployed on them. So let's go and deploy DAS on the existing fibre. So we didn't have to deploy anything, it was already there. And you can see that rig had those 2 fibres with those geometries coming off of it. And you can see you have about 1 kilometre water depth through the sea floor and then through the fibre going through a wet tree down to the depth of 21,000 feet. We took that, we stayed there for 7 weeks, we took 70 million traces all told on that fibre. 1,400 channels on each fibre. These are the cross sections we got. Again, of course, this is on the production string. You don't really want to put it behind the casing on an offshore well. So these were taken on a production string. These are the responses you get. And this is the processed results that Shell have got to date using that VSP fibre. What they're currently doing is they're comparing that result with the nodal survey results that they got. But there's a high degree of confidence that this is an extremely powerful new tool for them because it was done essentially with one guy sat on a rig with 2 boxes, sat there reading books for 7 weeks. And as far as our equipment was concerned, there was no more than that. So it's an extremely low-cost, rapid way of gathering data. What can we use it for other aspects then? Come on, is it going to work? There we go, I think the battery's dying. So I just wanted to show you in a borehole some of the other things you can see. This is what we typically see with a fibre down. We've got depth and time. And this is the waterfall that we get when a perforation detonates. And you can see the reverberation of the sound up and down the well as that perforation is detonated. The reason I show this is because on neighbouring wells we can also listen to that perforation on the DAS fibre. Because we've got full synchronisation, we can do very, very accurate velocity profiling between the individual wells using this data. So that's kind of a freebie that you get. So on the microseismics, we see large microseismic events. They happen to be mainly of the larger magnitude. So the smallest magnitude we've seen is about minus 1.75. That's because we simply haven't got the sensitivity of a geophone yet. However, what we have found is that it's extremely good at measuring these larger magnitude events. And this is a particular one. This is a reactivated fault that was generated. It produced very high magnitude event, but also at very, very low frequency. So the microseismic geophones in there were actually overloaded and couldn't actually resolve this properly. But we were able to see it on the fibre right the way to surface. You could see the P and the S wave very, very clearly. Now, fibre is, of course, is a one-component system. We've only got response in essentially one direction. But the fact that this well had a shape on it meant that you could resolve the position in these circles, and you could actually resolve in three-dimensional space where the event actually happened. So because this is permanent now, you've got a way of permanently monitoring your wells and looking for these larger reactivated faults using that fibre. So what could we do for seabed applications? Well, it certainly has got the potential to be used on land, and certainly ourselves along with Shell have been looking at some of the applications of this. We're burying these cables for things like seismic applications, where you bury them under the ground, leave them there, and then have these sources continually operating to see how the the field is being developed with the steam that's being injected in there. However, there is an issue with fibre as it stands at the moment, and that is the fact that fibre straight in its deployed linearly, as we have done to date, is very, very sensitive in line. Hence, it's ideal for VSP measurements. But it's not particularly sensitive cross-axis. It has a weak response in that particular area. And this plot really shows that. So as I say, very good sensitivity inline, poor sensitivity cross-axis. But there is a very simple way of overcoming that, and that's you start to wind it into a coil. So essentially what you're doing, if you create a 30-degree slope on that fibre, you can actually create, in effect, an elongated hydrophone that can be many kilometres in length. And you could set that hydrophone on the seabed. It would obviously be very, very low cost. And we believe it could be used for things like PRM systems for seabed and for land. And ultimately, we could put a coiled system in a well and get the sensitivity that we require for microseismics. We're also not just working on the cable design. The main thrust of our activity is actually on the box. So as I said, we started this in 2009. We went to a well, and that's the response we got, which wasn't particularly good. We came back, developed the box a bit further. 2010, this is what we got on the same well. 2011, this is, again, we repeated the test, and this is where we were up to. So you can see we were getting very, very rapid progress in developing this technology. Where are we today? Well, later this year, we'll be releasing our 4th generation, ODH4, and that will give us another 6 dBs of sensitivity, more channels, more dynamic range to play with. But we've also already started work on ODH5. And ODH5, coming out hopefully by 2016, should give us the sensitivity and performance of conventional geophones. So we'll have 10,000 channels, full dynamic range, full sensitivity of a conventional geophone. And that really does then begin to open up the space for what this technology can do. So in summary, DAS is commercially available as a VSP acquisition tool and is being used by Shell and quite a few other major oil companies now. It enables borehole measurements to be made in extremely difficult, in wells that would be almost impossible and far too expensive to be done using conventional geophones. It provides on-demand seismic acquisition, because when it's permanently deployed, you can now therefore do time-lapse measurements easily and at low cost. And so for 4D programs, it's especially useful, and it's being looked at as an enabling technology in lots of EOR applications. And with further development, we believe that this technology will be used in situations like PRM, land seismics, and furthermore for microseismic developments. Okay, that's it. Thank you.
Well, thanks very much indeed, David. In fact, if those of you who went to the EAGE had attended a Shell paper by Case Hornman, you would have heard about how this system is implanted permanently in an old field that had been decommissioned and has been re-extended its field life to a place called Schonebeek in eastern Holland. So there are lots of applications out there, which is very impressive, really. Okay, so time for a question or two or three. Whose is the first? Yes, please.
Paul Mayton with Selimonite. I know these things are put into wells and for DTS, permanent installations in wells for DTS. Could you come along and plug your box on instead of the DTS box? Use the same fibre? Is it capable of being one fibre being used for several different applications? Or
generally, yes. DTS tends to use a slightly different fibre type called multi-mode fibre. Many of the DTS systems, however, are moving over to single-mode fibre. So the difference in commonly is multi-mode is what we see in building infrastructures, whereas single mode is what we use for transmitting our phone calls across the Atlantic. So the core of the fibre is different. But we have done that. We have used different, we have just transferred a DAS system onto a DTS fibre. Commonly, however, most of the time now, cables are being put in with both types of fibre. So we run them side by side.
thanks.
Please, yeah, Hugh Abbott. More exercise for Adam.
Hugh Abbott, CRA Maricon. Dave, if you are faced with a skeptical drilling engineer to put one of these fibres in, as you said, the cost of installation varies depending how you put it in. What do you say to them to try and get them to what you say is the benefit, the value of getting this in?
Absolutely. It always is a challenge to get any individual discipline to want to take the upfront cost of putting the fibre in. Our challenge is to go into all of the disciplines, from completions to production through to the evaluation people as well, and say the cost of putting that fibre in and then being able to do all of these measurements, flow and hydraulic frac monitoring and everything else in your well is extremely beneficial. However, with a lot of these jobs now, because we're putting the fibre on the production string, the cost is actually considerably lower anyway, because they're doing it as part of their refit of the well. So as they're pulling it out, they've already got gauges on there. Sticking a cable on for fibre is actually extremely low cost in comparison. So that seems to be the balance, and hence that's why the PDO job has gone ahead with 8 wells. It was a significantly lower cost than doing it in any conventional way.
I used to have a well survey unit, and we'd go out in a rig, and the driller would say, "You're going to put that down my well," but a fibre I wouldn't have thought would be so much of a problem, actually. Anyway, next question. Yeah.
Vincent Shepherd from Petrofac. Really interesting talk, thank you for that. Just a quick question on changes to the sources that you would need to make in a VSP acquisition with the fibre. What would be the main changes?
Changes to the sources?
To the source on the surface?
We don't change the sources at all. So we've used vibra size, accelerator weight drops, dynamite. They're standard sources. Mm-hmm. The only thing we would do is more effort. So in terms of a vibra size, we would maybe sweep twice. Instead of 2 times, you may do 4 sweeps, for instance, just to get some more source effort into the ground. And that's simply a function of the fact that the fibre's on the production string rather than good coupling behind the casing. But we've used all sources, and we fully integrate with them all as well. So hence, we control those sources. Hence, we're able to do the stacking correlation all in real time.
Well, it's still quite silent. There's not much rumbling of stomach, so there's time for another question. Yeah.
Steve Pickering, Slumbershire.
Sorry.
Yeah, sorry, Ian. So the question I had was, you talk about stacking to build up the signal to noise. What sort of pseudo interval of some shots records do you produce?
The number we stack? Well, typically if there was 4 sweeps, 4 stacks.
Oh no, that's on the source side. But do some you take an image, you said you build up the signal to
No.
noise because you have a continuous recording.
No, it's just, you just take the 4 individual shots and just stack them together. There's no other summing necessary.
Okay.